Now we've looked at using first order separable differential equations and the theory behind the general idea with them. I wanted to talk to you in this video about how we can use and apply these methods and methodologies in order to be able to look at modelling scenarios using differential equations. Now this is an important application of this technique that we have to be able to work with. You know, in many subjects, particularly things like engineering, computer science, the various sciences, so physics, chemistry, biology, what we want to be able to do is take a scenario and the information given to us, apply methodologies and techniques using differential equations, and be able to solve them for any particular scenario that may come up. So we may be given some particular conditions that it has to satisfy or at a certain point in time, and we have to be able to solve it and come up with some sort of differential equation, an eventual equation, that helps us model that scenario and lets us predict long-term behaviour or any upcoming behaviour depending on what the situation is. Now this is the kind of topic I could sit and talk to you about for ages, go on about a whole bunch of spiel and jargon, but I reckon the best way to show you this is to actually show you a couple of examples, talk you through them and have you think about the kind of things that may pop up. Now the first one I'm actually going to focus on what's called Newton's law of cooling. Now this states that the rate at which an object cools is proportional to the difference between its temperature and that of its surroundings. Now what I'm going to do in this scenario is let capital T be the temperature difference at a time t, so little t. What I'm also going to tell you is that the temperature is initially T naught. And what I want to do is express this T in terms of little t. Now a key thing you have to do is looking at this first sentence and look at the fact that it's proportional to the difference between its temperature and that of its surroundings. So the rate at which the object cools is proportional to that. So this is what allows us to set up our differential equation, because knowing this, what I can tell you straight away is that dt, so the rate at which the temperature changes with respect to time, that's going to be proportional to this capital T, the temperature difference at the time t. Now using that, what I can do is actually set up an initial equation where I've got dt by dt is equal to kt. Now I can set it up with a general constant k because I know since it's proportional to this value t, it's essentially going to be something times this value, regardless of what that something is. So I can set it up using this. Now what this then allows me to do is take this, create it into a first order separable differential equation, so split it onto both sides, and solve it such that I can get a solution which I can then hopefully express as it wants me to. So what I can do with this is if I take all the capital T's to one side, all the little t's to the other, what I can say is dt by big T is equal to k times dt. So now that I've got that, and I know this, what I can then do is expand it and say that the integral of both of these sides must be equivalent. Now this is essentially 1 over t, so what that tells me is that ln of capital T equals the integral of k dt equals kx plus c. Now I'm going to get rid of the logarithm here because what I want to do is express capital T in terms of t, so all I want left on this side is t equals. So I'm then going to say fine, so I know then from that t equals e to the kx plus c. Now remember, when you get anything in this format here, split it up using our rules of exponentials, so I'd have it written as e to the power of kx times e to the power of c, and then take this e to the power of c and represent it again by a generic constant. So I can take that and rewrite it as t of little t equals a e to the k t. So what that now means is I've got my general solution to this differential equation. However, what I'm given is this condition here, that initially the temperature is T naught. Now what that means then is initially, so time is t equal to 0, my capital T is equal to T naught. So what I can do is substitute these into this here, and I can then say fine, so what that means is T naught is equal to A times e to the power of 0. Well, e to the power of 0 is just 1, so I can tell you that a is equal to t naught. So this allows me to then rewrite my equation as t of t equals t naught e to the power of k t. Now this is the kind of question that could be expanded upon, so you could be given a value for this initial temperature. You could then be given a time at which things are valid and the temperature you have at that point, which we can then use to calculate this constant k. In this question though, this is us, this is where we want to get to for our solution. Just bear in mind we may then get a second part that has us expand on what we've got and use the equation we've just found to then eliminate any extra constants that are in it, or apply it to a set scenario and a set of conditions that we have to then solve. A second example I wanted to show you is this one here. So I'm going to tell you it's suggested that the rate at which a rumour spreads around the school is proportional to the number of students who had not heard that rumour. Now imagine there are 1,000 students at a school. What we're going to do is take capital N as the number of students who had heard the rumour on a day t. N naught is the number who initially knew it. What we want to do is we've got two parts. We want to express n explicitly in terms of t. And what I'm also going to tell you is that n naught equals 10, n1 equals 100. What is the value of n10 to the nearest day? So this is the kind of question that I'm going to apply this to. So it's a bit of an expansion on what we had previously and a different scenario, but in terms of the general steps, it's actually not too different. So first thing we need to do for part A is express n in terms explicitly of t. So if we read the question again, what we know is that the rate at which the rumour spreads around the school is proportional to the number of students who had not heard the rumour. Now if we take n to be the number of students who had heard, and we know there's 1,000, what I can then say to you is that dn by dt, so the rate at which it spreads around the school, is proportional to 1,000 minus n, because what that'll do is that'll give me the number of pupils who had not heard the rumour at that point. If I've got 1,000 in total, n had heard it, that's what it will be. So I can then rewrite this as dn by dt equals k times 1,000 minus n. So I can use the same set of steps at this point as I did previously, separate it out, and then calculate my solution from there. So I'm going to take everything with an n across here, and what I'll end up getting is dn over 1,000 minus n equals k dt. And again, same as before, because I know those two sides are equal. If I integrate, I know that the solution to that will also be equal. So what I can then say is, fine, if that's the case, once I've integrated, negative ln of 1,000 minus n is equal to kt plus a constant c. What I now have to do is figure out what my constants within this are. Now at this point, what I'm actually going to do is here, I'm going to start to look at substituting in, because if I can get a value here for my c, it'll actually make my working a little bit easier, particularly with this negative here. Now what I'm going to do is, if I look at this here, I can tell you that the initial condition is n naught to begin with. So what I know from that is that at t equals 0, n equals n naught. So what that means is if I substitute all of that into here, my kt will disappear, I'll just have my c left, the n will become n naught, so what I can then say is therefore c equals negative ln of 1,000 minus n naught. So I can rewrite this entire equation as negative ln of 1,000 minus capital N equals kt minus ln of 1,000 minus n naught. So that there's a fun looking equation. What we have to make sure we do is get everything with an n on one side and everything without the n, so with the t's, on the other side across there. So what I'm going to do is take this ln 1,000 minus n naught across to this side. I'm going to leave the kt here. So what I'll end up getting is the ln of 1000 minus n naught, take away ln of 1000 minus capital N equals kt. Combine these, use my rules with logarithms. So I've got ln of 1000 minus n naught over 1000 minus n equals kt. And again, get rid of the ln by taking it across an exponential on this side. And I've got 1000 minus n naught over 1000 minus n equals e to the power of kt. So I've got that written there as my equation. What I now need to do is express n explicitly in terms of t. So if I'm going to look at doing that, what I can do is multiply across by the 1000 minus n, and what I'll get is 1000 minus n times the e to the power of kt equals 1000 minus n naught. Take the e to the kt across, and that will then become 1000 minus n equals 1000 minus n naught over e to the kt. What I can then do is take this 1000 across here and combine the entire thing into one fraction over a common denominator. And if I was to do that, what I then end up getting is that n of t, my equation for n expressed explicitly in terms of t, is given by 1000 e to the kt minus 1000 plus n naught all over e to the kt. We get there after playing about with this and a little bit of jiggery pokery. Now that I've got that there, I can now look at part B. So for part B, what we're told is that n naught is equal to 10, n1 is equal to 100, and what I want to know is how many it is on n10. So what we're going to do here is we're going to use that second condition of n1 equals 100, and I'm going to substitute the values in for that. So I know that n of t is equal to 100, and I know that the t's are equal to 1. So I'm able to say then is that 100 equals 1000 e to the k minus 1000 plus my n naught. Well, I know my n naught is my initial value, which is 10, plus 10 over e to the k. So what I've now got is an equation which I can muck about with and find out what the value of k is. Now if I multiply e to the k up to there, I get rid of it as a denominator. What I'm then going to do is get everything with an e to the k on one side, everything without an e to the k on the other side. What that then ends up giving me is I can calculate that I get 1000 e to the k, take away 100 e to the k equals 1000 minus 10. So I can then simplify both of these here. That will then end up giving me 900 e to the k on this side equals 1000 minus 10, so 990. Divide through and I get the e to the k is equal to 990 over 900, which is equal to 1.1. So now that I've got it, what I can do is take it and substitute it back into the original equation for any e to the k. What that then means, I can rewrite the original equation as n equals 1000 times 1.1 to the power of t, take away 1000 plus 10, so my initial condition n naught, all over 1.1 to the power of t. So that's me got the equation. I now want to know what it was like on day 10, so t equal 10. So for that, all I do is I substitute in the values. I'll substitute in the fact that t equals 10. What I'll end up getting for that is 618 to the nearest whole number, so 618 people. So we've used our differential equations to model this scenario and taken our initial conditions to then get this to a point where we're able to work with it in a more effective manner.